right? This is APAB, and we are doing section 1.5, which is infinite limits. So basically limits that involve infinity in one way or another. And we're going to break this down into two basic categories of limits. So the first kind we're going to talk about is limits at vertical asymptotes. So when we did 1.2, we talked about how your book inexplicably says in 1.2 that limits that go up forever don't exist because they don't actually reach a numerical value. And I said to you that I wasn't going to teach you that because in like 3 sections they were going to reverse that and tell you the actual truth. So let's look at what we see as behavior around vertical asymptotes. So here's how vertical asymptotes look, right? So vertical asymptotes, a visual. So here's a visual of the way vertical asymptotes generally look, right? Sometimes vertical asymptotes look like this. So I'm going to put an asymptote at x equals 1, and we're going to go ahead and have this go this way and this go this way. Okay, so this is the graph of 1 over x minus 1 for the record. But okay, so here's a vertical asymptote at x equals, let's say, 1. Great. Okay, another way that vertical asymptotes can look, right, could be the other direction of mismatch, right, where I have this one going up and this guy going down, right? But see how this guy's going up to positive infinity and this guy's going down to negative infinity. This guy's going up to positive infinity and this guy's going down to negative infinity. Okay. Another way that this could look is that both of the directions could be the same, right? So like this guy could go up to infinity and the guy over here could also go up to infinity. Cool. Okay. And then the, sort of the fourth option, and I will have a caveat to that in a sec because there is actually one other option, right, is that they could both go down like this, right? So down and down. So negative infinity and negative infinity. Okay. So there are 4 main options. Now, the caveat I'm going to give you to that is that there are certain specific cases where a function literally only exists on one side or the other, okay? So, and we'll talk about that. For instance, a natural log function is a really good example of something that has a vertical asymptote and just doesn't exist on the other side. But let's assume that these are the 4 major options we're looking at, okay? So if we look at this option, if I asked you, so I'm gonna tell you that this is x equals, I don't know, let's call that x equals 2. Let's call this vertical asymptote at x equals 1 again, and let's call this vertical asymptote at x equals 5, because who cares? Doesn't really matter. Okay, so I just gave you numbers. If I asked you to look at each one of these situations, and I asked you visually, what's this limit doing? Well, in this graph, the limit as x approaches this x value, which is 1 from the left of this function, let's just call it f of x, is a negative infinity. But the limit as x approaches 1 from the right of this function is a positive infinity, right? So the double-sided limit would not exist, right? So essentially, the limit as x approaches 1 of this function would not exist, right? Does not exist, okay? So that's that first case. So let's just call this f of x. Just to make it easier, I'll call this graph g of x. We'll call this graph h of x. We'll call this graph j of x. That's not an x, but you get the idea. Okay, so the idea here is that when you're looking at asymptotes, there's really only a couple options, right? Basically, when you look at asymptotes, the graph goes to positive or negative infinity. If the graphs go to opposite infinities, then the double-sided limit doesn't exist. So if we look at this graph of g of x, right, this graph that's right here, the limit as x approaches, I called this value x equals 2, just because I picked 2. From the left of g of x, from the left, this guy is definitely going up to infinity. The limit as x approaches 2 from the right of g of x, well, this graph is definitely going down to negative infinity, which means that the double-sided limit as x approaches 2 does not exist, right? Because the 2 sides aren't the same. If we did the same thing here, well, they both go up, right? So the left limit is going up, the right limit is also going up. So all 3 limits, the left, the right, and the double-sided limit, would all be a positive infinity, right? The limit as x approaches, what do I call this? I call this 1 again. 1 from the right, from the left, doesn't really matter, of h of x would be an infinity, and the limit as x approaches 1 from the right of h of x would be an infinity, and that means that the double-sided limit, the limit as x approaches 1 of h of x, would be infinity, because they went to the same infinity, right? And then the same thing would be true over here, right? My left-sided limit, I called this x equals 5, just arbitrarily. The limit as x approaches 5 from the left of j of x would be a negative infinity. The limit as x approaches 5 from the right of j of x would be a negative infinity, which means the double-sided limit as x approaches 5 of j of x is a negative infinity, okay? So if you're looking around an asymptote, your limits are either going to infinity or they don't exist, right? Positive or negative infinity, or they don't exist. Those are pretty much your only options. Now, a little caveat about that, right? Let's buy myself a little space here. So just a little bit of a weird case, right? Remember, we did talk about what happens if there is no left side or right side, like if a graph ends. So in the example of something like f of x equals the natural log of x, this graph has a vertical asymptote at x equals 0, which I'm going to draw big obnoxious dots for, and then doesn't exist on the other side. So this limit, the limit as x approaches 0 from the right of f of x is negative infinity, but that's also the same as the double-sided limit because there is no other side, right? So there is no left side. So there's no left limit, and if there's no left limit, then the double-sided limit's just the same as the right limit. That only happens with a handful of functions. I just wanted to show you that that's a thing, that that there is no left limit in that case, so the right-sided limit is the same as the double-sided limit. Okay, so now knowing that, let's talk about what we do if we have an equation at a vertical asymptote and how we can figure out what the value of the limit is. So I'm going to erase these and then just draw tiny versions of them off to the side. Okay, so really I have these four basic options, right? I have the mismatch, so one side down, one side up, right? I have the other mismatch, this side up, this side down on the vertical asymptote. I have both go up, and I have both go down. Those are really the four options that we're looking at here. And I'm just going to keep them over here, 1, 2, 3, 4, so that we can kind of reference them as we're doing stuff, okay? So let's go ahead and call this example 1, all right? And we're going to evaluate the limit. Okay, so let's do the limit as x approaches 3 from the left of 2 over x minus 3. Let's do the limit as x approaches 4 from the right of a 5 over x minus 4. Let's do the limit as x approaches 2 of negative 3 over x minus 2. And I'll give you one more. We're going to do D. Let's do the limit as x approaches negative 1 of a 4 over x plus 1 squared. Okay, great. Okay, so we'll see if I end up running out of room to do these. Okay, so there's a couple options. Some of you might be thinking, hey, you know what? The easiest option is just to graph this. Like, look, if I graph it, I'll know which of these four it is. Boom. The thing is that graphing is tedious and frustrating, and if you have a calculator, great, typey, and you're done, right? So to be clear, if you have a calculator, type this thing in, look at what's happening as you approach 3 from the left, boom, you're done, right? If you don't have a calculator, here's the way you can deal with this. You say, okay, cool, I get it, 3 is the vertical asymptote, right? I understand that 3 is the vertical asymptote. I'm going to pick a couple values to the left of 3, so 2 and 1, just nice, easy values, right? I'm going to pick a couple values to the right of 3, so let's do 4 and 5, okay? Now, again, you could just plug this in a calculator and visually look at it, but you're not always going to have a calculator. Oh, sorry, I don't need the, this says from the left, ignore the right values. It just said from the left. I was doing what I would do over here when there's a double-sided limit. So I pick values to the left. So I only need a couple values. I pick ones really close to 3, right? And I'm going to pick a couple values. Now, if you look in your textbook, okay, so your book is totally going to be like, yo, you should pick 2.999 and 2.99 and 2.9. Okay, great. Here's my argument. If you're picking these numbers, you're definitely using a calculator, right? And if you're using a calculator, why would you make the table? You would just graph it and be like, I have eyeballs, right? You'd pick which thing's happening. So, like, this is not an option without a calculator. So while your textbook is telling you, yeah, totally do this, right? Why? If I had a calculator, so if I have a calculator, I'm going to put into my y1 2 divided by x minus 3. I'm going to graph it, and I'm going to see that it looks like this. And I'm going to be like, oh, sorry, that's backwards. I'm going to be like, oh, look, that's a negative infinity. Cool, that's my answer. Like, I'm not, why? I wouldn't do this if I had a calculator. I would just graph it and be like, yo, I have eyeballs. So The reason I say that you should pick easy x's to the left is because we're assuming you're doing this without a calculator, because if you had a calculator, you'd just graph it, right? So I picked two very close values to 3. In fact, the easiest, laziest numbers that I can pick. So I pick the easiest numbers that I can pick that are to the left of 3, which in this case is 2 and 1, right? So I get 2 over, when I do 1 minus 3, I get negative 2, so that's a negative 1, right? And when I plug in 2, I get 2 over negative 1, which is negative 2. Here's my point. These numbers are either trending down, meaning they're going to go to negative infinity, or they're trending up, meaning they're going to infinity. I already know that the side, like as I approach an asymptote, I'm either going to go to an infinity or a negative infinity. Those are the only options. Since negative 2 is lower, this thing must be going down. Sure, negative 2 is nowhere near negative infinity, but when you compare negative 1 to negative 2, your values are getting lower as you approach the vertical asymptote, so I'm approaching negative infinity, and that's my answer. Now, you would have figured the same thing out if you used like 2.9 and 2.99 and 2.999, but you would have needed a calculator and you would have been miserable. This does not work for other limits that could be approaching other random values, like 2.57, right? This works because we know ahead of time, given that this is a vertical asymptote, that the only possible answers are infinity or negative infinity. That's it. And when you get over to the double-sided limit, it could be does not exist if the two infinities don't match. That's it. So knowing that I have to be getting an infinite answer, I just compare the numbers, and as I get closer to the asymptote, I'm going farther down, therefore I must be going to negative infinity. Let's do the same thing over here. This is the right-sided limit at 4, right? So I pick two easy numbers that are to the right of 4, right? The easiest numbers I can pick are 5 and 6. Again, I know my answer is either a positive or negative infinity. That's it. Because it's a right-sided limit, it's not even a does not exist possibility. It's either a positive infinity or a negative infinity. So I get 5 over 1 and 5 over 2, right? So this is a 2.5 and this is a 5, which means as I approach the vertical asymptote, sorry, I drew down and I meant to go up. 2.5 is lower than 5, so I'm going up forever, right? As I approach the vertical asymptote, the numbers are getting higher, so this thing is going to infinity, right? Now the double-sided limit is going to involve me having to make a two-sided table. So I did A and I did B. I'm going to erase this work so that I can do C with a little more space. So when I go to do C, my vertical asymptote's at 2, right? So I need stuff on both sides because it says the double-sided limit. So on this side of 2, I have 1 and 0, right? On this side of 2, I have 3 and 4. Again, I'm just picking the easiest values. It's not wrong to pick values that are closer to 2. You could pick 1.999 and 1.9. It'd just be a weird choice if you don't have a calculator. And remember, if you have a calculator, you'd just graph it and use your eyeballs. So now I'm going to go ahead and plug in, and I get negative 3 over negative 2, which is a 1.5, right? When I plug in 1, I get negative 3 over negative 1, which is a 3. Okay, so this side is getting bigger as I go towards the asymptote. So this side's approaching a positive infinity. When I plug in over here, I get a negative 3 over 1, which is a negative 3. When I plug in the 4, I get negative 3 over 2, which is a negative 1.5. Negative 1.5 is bigger than negative 3, so as I go this direction, I'm going down. So my answer to C is does not exist because I have opposite infinities, right? It's one of these situations where I have a positive infinity on the left and a negative infinity on the right. Let's do D in the same way, and then I'll give you a practice problem to try. All right, so when we go to do D, I'm looking at negative 1, and I can see that's an asymptote because if I plug in negative 1, I get a 0 on the bottom. So negative 1's in the middle. I pick numbers to the left of negative 1. Well, that's going to be negative 2 and negative 3. Pick numbers to the right of negative 1. That's going to be 0 and 1, right? And then just plug in and see what the trend is. And again, it's helpful to label this as a vertical asymptote because remember, you're coming from the sides, and you're going to see what you do as you approach the vertical asymptote. So let's plug in negative 3. When I plug in negative 3, I get a 4 on top of a negative 2 squared, which is also a 4, so I get a 1. When I plug in a negative 2, I get a 4 on top of a 1, so that's a 4. Well, that means that these values are going up, right? Because as I go from 1 to 4, my values get higher, so that's an infinity. And again, if it helps, you can draw it down here. It's going up like this, right? Okay. And then when I plug in 0, I get 4 over 1, which is a 4. And when I plug in 1, I get 4 over 4, which is a 1. So again, my values are going up. Both sides are going to infinity, so that means the double-sided limit is infinity. Okay? All right. So let me give you a P1 that's the same basic concept. Again, I'll leave these 4 diagrams up here so that you can see them. Notice that if you're asked to find the double-sided limit, you have to consider both sides. All right, so for A, let's do the limit as x approaches -2 from the left of a -1 over x plus 2. For B, I'm going to do the limit as x approaches 0 from the right of a 3 over x. For C, let's do the limit as x approaches 2 of a -1 over, actually let's do -10 over an x minus 2 squared. And for D, let's do the limit as x approaches 1 of a 4 over x minus 1. Cool. All right, so, and that's your P1. So you can pause me if you want. I'm going to go ahead and walk through them. So is a screaming baby waking up from his nap upstairs. So pause me if you want. I'm going to walk through them. You can give it a try. All right. I recognize that I may not have enough space to squeeze all these in, but I'm going to try. All right, so for A, I only want values left of -2. So here's my -2, right? That's my vertical asymptote. And I need numbers to the left of -2, which are going to be -3 and -4, right? So when I plug in -4, I'm going to get a -1 on top of what seems to be a -2. So that's a 1/2, right? When I plug in -3, I'm going to get a -1 on top of a -1, which is a 1. That means these values are getting bigger, right? Because 1/2 is smaller than 1, so my answer is infinity, right? When I do values to the right of 0, right? So here's my 0, which is a vertical asymptote. I want numbers to the right of that, which would be 1 and 2, right? Easy numbers to the right. When I plug in 3 over 1, I get 3. When I plug in 3 over 2, I get 1.5. That means that these values are getting bigger, so this is also an infinity. When we do this one, we need both sides, right? So I'm going to go ahead and put my 2 with my vertical asymptote in the middle, right? So I need some values left of 2, which are going to be 1 and 0. I need some values right of 2, which are going to be 3 and 4, right? So when I plug in 0, I seem to get a -10 over 4, which is like a -2.5, okay? When I plug in 1, I get a -10 over a 1, which is a -10. That means that this is going down to -infinity, right? Because -10 is smaller than -2.5. When I plug in 3, I seem to get a -10 over 1, which is a -10. When I plug in 4, I seem to get a -10 over 4, which is, again, that -2.5. So again, my values are going down. So both sides are going down to -infinity, which means my double-sided limit is -infinity. When I try to squeeze in, let's see if we can squeeze in D up here. Okay, so let's put D up here, right? So for D, right, I'm working around 1, and I want the double-sided limit, so I need values left of 1, which will be 0 and -1. I need values right of 1, which will be 2 and 3. When I plug in -1, I get 4 over -2, right? 4 over -2, which is a -2. When I plug in 0, I get 4 over -1, which is a -4. So these values are definitely going down as I approach the vertical asymptote, right? Because -4 is lower than -2. When I plug in 2, I get 4 over 1, which is 4. When I plug in 3, I get 4 over 2, which is 2. So these values are going up. So that means that this limit does not exist because the two infinities are going in opposite directions. All right, so that is our first video in 1.5. In the next video, we're going to talk about what happens when it's x approaching infinity instead of the outputs.